we are going to continue with keyword spotting on microcontrollers and embedded Linux devices. An example of a microcontroller is this ESP32, which is a 32-bit microcontroller, 240 megahertz of clock frequency, 520 kilobytes of RAM, right? It's a tiny device, as you can tell. It has a RISC CPU, and unlike this embedded Linux device. This is a Raspberry Pi 2. It has an ARM chip on it, right? Should be ARM version 7, right? That's what we have on here. And then we can deploy our keyword spotting model on it, even though it's a constrained device. Let's go over the architecture of a keyword spotting model, right? The inputs, as we discussed in the last video, the inputs to these kind of models, to the keyword spotting model, that is an image, but that image is spectrogram, right? And as we can see, it's an image that shows the frequency of the components within the keyword itself. So that's feature extraction that we do from the waveform. So that's why we need to compute the fast Fourier transform on the waveform to get the spectrogram, which we then feed into a convolutional neural network. In this case, that's the base model that's extended to have additional layers, dense layers, and then each output really represents the number of keywords we have. So if we want to have a keyword, say Sheila, then that keyword then is the only keyword we're interested in. Anything else we can say it's a 0. So in that case, we will need 2 output neurons. So we're gonna go over code that does that, and then we'll deploy it on a Raspberry Pi, right? In that case, we'll be deploying it on a Raspberry Pi 3B, and we can also deploy it on here, right? If we have a microphone, but we will show all the processes and steps taken to deploy a model on these devices. We're gonna go over training a wake word detection model. Just continuing from the last time, same code. We're using Kaggle to get our Google speech commands dataset, and within that dataset there's a keyword that we want. We haven't gotten to that part yet, but for now we just want to have a general training to see how that performs. So now, after unzipping the Google speech commands dataset, we can check it out. We see these are the commands that are in it, right? So we can pretty much pick any of these or add our own to be our keyword. But in this case, I'm going to use Sheila, which happens to be my mother's name. But we'll do that in the next video. I'm going to show you the waveforms. We can plot the waveforms of each of the words, right? So this is time and amplitude of the sound. This is hard to get information from, so we can convert it to, we can change the domain to frequency domain using the short time Fourier transform. That's what this code does. So we have TensorFlow that allows us to get the spectrogram, or you can define your own function really to do that. And then, for example, left has this spectrogram as we saw in the last video. This is now time and frequency. We can check for every other word, and then we build our own convolutional neural network that we're going to feed this data to. And this is our model, and this is the architecture of the model, right? You can see it right there, and this is useful information we can get from it. We have trainable parameters of about 1.6 million, which is 6.21 megabytes. But remember, we want to deploy that on a microcontroller, and we saw that the ESP32, for example, has RAM of 520 kilobytes. Okay, so now we can compile model, then we train it. Our accuracy starts very low, as you see here. Our accuracy is at about 25%, then it goes all the way to 84%. That's it. We save our model as an H5 model, and we load that model to convert it to TF Lite. That's what we're gonna do here. We run that, and this is what we get, and then we save the model. That's it. So that's how you save the model to TF Lite, which is a TensorFlow Lite version that runs on microcontrollers, mobile devices, and embedded Linux devices. As you can see here, we have our normal model and H5 model, and we also have our TF Lite model, which is a compactified version of the H5 model. So next thing we're gonna do is we can deploy this model as is, the TF Lite model, on a Raspberry Pi or any embedded Linux device, or we can actually convert it further to TF Lite Micro and deploy that on a microcontroller like an Arduino or an ESP32. So now that we've saved our TF Lite model, we can then convert it further to a C++ file that we can deploy on an ESP32 or an Arduino. And this C++ file pretty much contains the data about the model, right? It's like the signature of our voice command model. So we run this command really to convert that TF Lite model into a model data.cc. There it is. We simply run it like that, and that's it. And we can check in our directory. We now have model data.cc, and then we can download it. I've already done so. So I will now show you what that looks like. And this will be our model data. As you see here, an array. It's this unsigned character voice command, and we have our hexadecimal numbers like this. This is what represents our model, and we can deploy it on a microcontroller. I'll show you how that's done in an Arduino environment. So we need to create a tensor arena, right? Initialize our model, and then that's it. So when we set our tensor arena size, and then we need to have our model. So for our model, remember, it's that file. So this is in Arduino. It'll look like this. So we can define other macros that will help in preparing our model. And this is our model data.